velocity profile under a turbulent flow, whatever I have seen that the form of equation of motion in the laminar and in the turbulent flow, there is a slight difference. The difference being that your all the dependent variables like velocity components and the pressure will be time averaged. That is number one. Number two is that you will be getting some extra terms in the Navier-Stokes equation for the corresponding turbulent flow. These extra terms are known as the Reynolds stress terms, and somehow you have to quantify them in order to obtain the velocity profile. So, there are semi-empirical and empirical relations available which will be giving you a relationship with the turbulent stress terms with the velocity or the gradient of the velocity. So, then you have to solve the equation in totality, then you will be getting the velocity profile. Now, we have seen some of the semi-empirical relationships. Now, there are four. One is corresponding to the viscosity. There will be an analogical equation for the turbulent coefficient of viscosity. That is number one. Number two is Prandtls mixing length hypothesis or a relationship that will be basically analogical to the kinetic theory of gases. The third one is von Karman's hypothesis or von Karman's relationship. It gives a relation between the the turbulent stress or the Reynolds stress with the gradient of the velocity in the following form. Where k being an empirical constant ranging between 0.36 to 0.4. Now, using this relationship, you will be getting some kind of velocity profile. If you compute this velocity profile with the other two, you will be getting almost close result. Now, there is one special form of relationship that will be available for flow near the wall. Near the wall, the viscous terms are dominant, and turbulent eddies will be comparable to the viscous, will be negligible compared to the viscous terms. Just beyond the viscous sublayer, that is called viscous sublayer. Beyond the viscous sublayer, you will be getting both the terms are equally important. Turbulent eddies and the viscous terms both are equally important, and beyond that, the turbulent eddies will be predominant, and the fluid particles at the core region will not realize the existence of the wall. That means, viscous forces are really pretty negligible in that turbulent core region. So, close to the wall, you will get Dirichlet's relation. It is a bit complicated. This gives an empirical relationship between the shear turbulent stress term or shear Reynolds stress term with respect to velocity and the gradient of the velocity. Now, close to the wall, you can this value y will be pretty less. Okay. So, exponential of this term will be very small. So, you can have an exponential expansion. Okay. So, that is very close to the wall. Beyond that, this term will be still there. Okay. Now, these four relationships of Reynolds stress with the with respect to velocity and the gradient of velocity can be utilized, can be inserted into the your equation of motion, and you will be getting the velocity profile. Let us have one derivation for the turbulent velocity profile for flow through a tube. This will be given to you. Now, we have seen that there you will be getting a distinct regime of velocity if you ever plot the velocity with respect to some kind of distance from the wall. This y is distance from the wall. In the log scale, you will be getting some kind of relationship like this, like this. So, close to the wall you will be getting a linear relationship. Okay. This is basically viscous sublayer. Beyond viscous sublayer, you will be getting a transition region where both viscous terms and turbulent eddy terms are equally important, and in the turbulent core, you will be getting the turbulent eddy terms only, where the viscous terms are really negligible. Now, this profile is known as the universal velocity profile. Now, let us define our coordinate system from the wall. So, S is the distance from the wall, it is defined as capital R minus small r. Okay. Now, now we will be getting this derivation in the turbulent core. First, we will be doing this derivation for the turbulent core, where the viscous terms, where the turbulent eddy terms are really important. After that, we will be doing this derivation close to the wall using the Dirichlet's relationship. So, first derivation, that is for turbulent core, we will be using the Prandtl's mixing length analogy. You can use any other relationship in fact. So, let us do first with the Prandtl's mixing length analogy. In that case, the component or the parameter L, that is basically k into y. In this case, it will be k into s. Y is the distance from the wall. Here we have defined s is the distance from the wall. So, s is exactly equivalent to y, whatever we had in the Prandtl's analogy expression. Now, let us write down the turbulent part or the Reynolds stress part of the shear stress that we get from Prandtl's analogy. Now, this is the expression for the shear stress term using Prandtl's analogy. Now, convert R to S coordinate. Okay. If you do that, then the expression of shear stress that you will get is this is equation number 1. Tau Rz, the turbulent part, the Reynolds stress term is equal to rho times k1 square, that is an empirical constant, multiplied by s square, distance from the wall, and time averaged derivative of time averaged velocity with respect to s. This will be with respect to s. Okay. From the equation of motion of steady state incompressible flow, what you will be getting is that if you ever solve that, you will be getting the left hand side will be equal to 0, the inertial terms, delta p by L, that is p 0 minus p at L divided by L minus 1 over R d dr of R tau R z, the time averaged one. This will come directly from the equation of motion, and how to simplify the equation of motion in the last semester we have seen enough examples. Okay. Now, this tau R z will be having two terms, two component. One correspond to tau R z for laminar one, that will be mu times gradient of velocity, another will be tau rz, the turbulent, correspond to the turbulent term, and this turbulent term corresponds to turbulent term is basically the Reynolds stress term. Now, you can integrate this equation you can integrate this equation with the boundary condition that shear stress is equal to 0 at the mid of the channel. That is quite obvious, because the middle of the channel the fluid particle will not realize the existence of the wall. So, shear stress will be exactly equal to 0 and it will be maximum at the wall. So, if you do that, the result will be no, this shear stress will correspond to the total shear stress, and at the middle of the channel, whatever it is, the shear stress originates from the wall effects. Okay, the fluid particles at the middle will not realize the effect of that. The turbulent term will not be equal to 0, will be forcing the viscous term will be equal to 0. And let us wait for the rest of the derivation. Okay. So, after integration, what you get is tau rz bar is equal to P0 minus PL by 2L R by R. So, this will be tau 0 1 minus S bar R. Okay. So, tau 0 is basically shear stress at the wall at S equal to 0. Okay. So, and this will be equal to P 0 minus P L times R divided by 2L. Now, there is an approximation here. The approximation is close to the wall the viscous forces are dominant, but we are not looking into that. Okay, close to the wall means S by R is pretty small, but where the viscous terms is dominant, that will be very close to the wall. If you look into the magnitude, S by R may be 10 to the power minus 6 or 10 to the power minus 7. Okay. Beyond that, both the viscous viscous terms and the turbulent eddy terms will be equally important. From that point onwards, we can say that the even turbulent core starts slightly beyond that. And typically, when S, the non-dimensional S is 26, then turbulent core starts. And if you ever compute what is the non-dimensional S is equal to 26, that value will be coming probably 3 order or 2 order of magnitude less than the compared to the radius of the channel, radius of the tube. So, there is a gross approximation here. The approximation is S by R is very small. In that case, what we can do, the right hand side of this equation can be replaced by tau 0 only. We will be assuming S by R is very small compared to 1. So, 1 minus S by R will be roughly equal to 1. Although this is a very bad approximation. So, you can solve this equation without taking this approximation, but in that case you will not be getting an analytical solution. But if you take this approximation, do the computation, do not take this approximation, do the computation, and then compare your result, in your output you will be seeing that there is almost no difference. Okay. So, basically S by R, even when turbulent core starts, that will be in the order of at least 3 orders of magnitude less compared to the radius of the tube. So, that is why this approximation is valid. Now, this tau rz, there are two components as we said, one is corresponds to the viscous forces, that is for the laminar one, and the turbulent one, and we will be neglecting the term corresponding to the viscous forces. So, the right hand side of this equation will be rho k1 square S square dvz ds whole square is equal to tau 0. Okay. or you will be getting dvz bar ds is equal to this v star, this has a significance, this is equal to under root tau 0 by rho, and the under root tau 0 by rho has an unit of velocity, and since this tau 0 corresponds to the shear stress at the wall, this velocity, this hypothetical velocity is known as the friction velocity. Friction means where the viscous forces dominate close to the wall, where the friction forces will arise. So, this is known as the friction velocity. Now, you can integrate this equation between some points, that is the edge of the buffer layer, or the buffer layer means the transition layer where both the terms are equally important, because this whole analysis is valid for the turbulent core. The turbulent core starts from the buffer layer onwards to the center of the channel or center of the tube. So, you have to integrate this equation from the edge of the buffer layer to any location in the turbulent core. So, the integration should be between S1 location is some location which is basically the edge of the buffer layer, and S is any location in the turbulent core. So, you will be getting an expression Vz is equal to Vz bar 1, that is the velocity at the edge of the buffer layer. We do not know that velocity till now, is equal to V star, that is the friction velocity divided by constant k1 of variation of logarithm variation of the distance ln s by s1. Now, in dimensional form, non-dimensional form, the velocity profile looks something like this. We will be defining all the non-dimensional quantities where the velocity is made non-dimensional with respect to the friction velocity, and distance is non-dimensionalized by with respect to friction velocity rho by mu. So, it is basically some kinds of Reynolds number with respect to the friction velocity. Okay. This one? Previous to that? The non-dimensional one. This v plus equal to v velocity is non-dimensional against the friction velocity. So, this Vz bar divided by V star, okay. And distance is non-dimensionalized. You cannot see this thing. Should I make it a bit larger? Okay. The S plus is equal to S times V star, that is the friction velocity multiplied by rho by mu. So, it is basically your Reynolds number defined based on the friction velocity. Okay. Mu we take as a constant, that mu is basically the physical mu of physical viscosity of the solution. It has nothing to do with the turbulent coefficient of viscosity. As I said earlier, from the experiments, edge of the buffer layer is taken as S plus equal to 26, and at that location of S plus, the non-dimensional velocity becomes 12.85. These values they come exactly from the experiments. So, by putting these values, we will be getting the velocity profile as 0.25 ln s plus 4 for s plus greater than 26, or this is equivalent to 0.25 ln y plus 4 for y plus greater than 26. This y, the coordinate y is exactly equivalent to coordinate s because it gives a distance from the wall. Okay. This is known as the logarithmic velocity profile. Okay. After that, we will see how the velocity profile. So, the velocity profile will be logarithmic. So, let us look in, since all these parameters are empirical, they are empirically determined, the nature of the profile is important, how it is varying with distance, whether it is quadratic, logarithmic, linear or what, that is important. So, in the viscous sublayer, it will be having some kind of variation close to the wall, that we will be seeing next to it, and beyond that the velocity variation with respect to distance, the distance from the wall is logarithmic in nature, that is important. Now, we will see the velocity distribution. Close to the wall. Now, near the wall, both contribution of the shear stress from the laminar and turbulent will be equally important. So, tau Rz bar will be equal to tau Rz corresponds to laminar one plus tau Rz bar corresponds to turbulent part. Okay. And you put the expression of this laminar and the turbulent part as well. The turbulent, the Reynolds shear stress close to the wall, we will be using the Dirichlet's expression because that expression is valid close to the wall. It is a complicated one. And we already had that tau Rz total will be equal to tau 0 into 1 minus s by r by solving the momentum balance equation of motion. Okay. Now, in this case, we can really approximate s by r is pretty small compared to 1. That means close to the wall, since s is the distance from the wall, close to the wall, the value of s will be really very small. And this is a very good approximation for this particular case close to the wall. Okay. Good and valid approximation. So, in this equation you replace tau Rz bar by tau 0 on the left hand side, and the right hand side you will be getting only one derivative, that is dv bar dr, and this can be integrated between the distance 0 to some s value, which will be basically edge of the buffer layer, and this non-dimensional s becomes 5 for the edge of the buffer, where the buffer layer starts at the end of the viscous sublayer. These values 5, 26, etc., which will be roughly meaning a demarcation of the different layers are clearly obtained from the experimental results. That is why all these expressions and the relations are semi-empirical in nature. So, the resultant expression becomes tau 0 is equal to mu dv bar dr plus rho n square vz s n square vz bar s by nu. you convert the r coordinate to s coordinate and you integrate between s, let us say from 0 to some s, let us say s2, okay. And in the non-dimensional form, this s2 is basically the distance, any distance within the viscous sublayer. Okay, so you can integrate between the distance 0 to s2 plus, and you will be getting an expression of velocity profile in your within the viscous sublayer or within the buffer region. Now, this s plus, you will see in the right hand side you will be estimating v plus on the left hand side by carrying out this integration, and on the right hand side you will be getting v plus again. So, how will you carrying out this integration? This integration has to be carried out by trial and error. On the, because you will be you would like to find out what will be my point velocity within the viscous sublayer. That means you know the upper boundary of S2 plus between 0 to, let us say 0.1, I would like to find out what is my velocity v plus at 0.1. So, your upper limit is fixed. So, what you have to do, you have to find out, you have to assume a velocity quantity on the right hand side and evaluate this integral. Evaluate the integral on the right hand side. Assume v plus, evaluate the integral on the right hand side because the upper limit of the integral is known to you, and check whether the integrated result will be equal to left hand side or not, your assumption or not. Whatever the value you have assumed, the same value you are getting after integration or not. If not, you have to iterate. Okay. That is one way of doing it. The simplest way may be you go to the differential form, dvz dr is equal to some function of vz bar and distance, and do a numerical integration by RK4, Runge-Kutta 4 or Euler's equation by something else. You will be getting the velocity profile within the viscous sublayer and the buffer region as well. Okay. So, there are two ways. Anyway, this if you assume a value of v plus on the right hand side and evaluate this integral knowing the upper limit and check whether the value you are getting is equal to your assumed value or not, again that will be an empirical numerical method. You have to do a numerical analysis and get the result. The best way of doing is you do a RK4 by which will be giving a solution of ordinary differential equation. That will be much easier compared to this one, this trial and error solution. Okay.
What is the basis of taking the approximation of V plus? So we will means how can we assume, on what basis are we going to assume V plus?
You assume any value of V plus by, if you evaluate this integration on the right hand side, it will be returning a value which will be in the same order of magnitude of actual V plus. Okay. So, the second assumption will be closer, the third iteration will be even closer, the fourth iteration may be closest. And the best way is if you do the RK4, if you solve the ordinary differential equation, the initial condition has to be known, otherwise you cannot initiate the integration. What is the initial condition? At s equal to 0, from the virtue of no slip condition, your Vz bar will be equal to 0. So, you can start the integration and do an write a code on RK4 and get the velocity profile at different points of S. That will be better. This value n is equal to 0.124, it is some empirical constant for smooth pipes. This is for smooth pipes. Really close to the wall where viscous forces are dominant, that is for very small values of S plus, the exponential term will be very small. So, we can open up this exponential term. If you open up this exponential term, the denominator of this whole of the integrand will become 1. Okay, just open up this exponential, retain the first term and neglect the higher order terms, because s plus itself is very small. So, s plus square will be further smaller, cube will be further even smaller. So, you can neglect the higher order terms apart from the term number 1. So, it will become v plus is equal to s plus for s plus lying in between 0 to 5. So, you will be getting a linear velocity profile in the viscous sublayer. If you look into this profile within this viscous sublayer, this part is really linear. You can approximate this part as the linear. Later on, the nonlinear part starts. Now, the proportionality constant, the constant of integrations will be obtained from experimental results from Nicoret's experimental results. You can evaluate the empirical constants and you will be getting the velocity profile as u plus is equal to y plus for y plus lying in between 0 to 5. It will be equal to 5 ln y plus minus 3 for y plus lying in between 5 to 30. For y plus greater than 30. In some book you will be seeing that this turbulent course starts from y plus equal to 26. In some book you will be finding it will be starting from y plus equal to 30, greater beyond 30. Actually, all these integration constants etc. and these values will be obtained from the experimental results. So, experimental results varies from experiment to experiment. So, they will be roughly equal to 25 or 30, something like that. Okay. But what is most important thing is the nature of the variation. Close to the wall, the variation is linear. Beyond the wall, the variation is logarithmic. That is the most important thing. So, these three velocity profiles for the three regions in the turbulent flow are known as the universal velocity profile. Okay. Now, this completes our a study of obtaining the velocity profile for a turbulent flow regime. Now, you will see the difference. If you plot the laminar velocity profile, it will be parabolic at the center and velocity will be decreasing and it will be dying down to equal to 0 to meet the no slip boundary condition at the walls. Now, for the turbulent core, for the fully developed turbulent flow, you will be getting almost a linear variation that is very close to the wall, then the logarithmic variation, and in the linear scale it will look something like this, and then again it will be close to the wall, it will be meeting to equal to 0 to meet the no slip boundary condition. This fully developed turbulent velocity profile, this laminar flow, and there is something called plug flow, where you can neglect the variation of viscous sublayer and velocity profile will be as if it is uniform throughout. Like in the turbulent core, your velocity will be having more or less uniform. Similarly, in the plug flow, you can neglect the variation of viscous sublayer. Okay, that can happen if you are handling with a highly viscous material. For highly viscous material, you can assume that it is almost like a plug flow. That means throughout the cross section of the channel or the tube, you will be having same velocity throughout, uniform velocity. There is no variation of velocity. For the laminar flow, velocity will be maximum at the center and it will be dying down to 0 at the walls throughout the cross section. For the turbulent flow, most of the part velocity will be roughly equal to same most of the channel, and at the close there will be sharp variation and it will be dying down to 0 to meet the wall condition. But in the plug flow, you can assume it is almost uniform velocity throughout the cross section. That you can realize for if you handle the flow of a highly viscous material like a toothpaste, something like that. Okay. Now, once we get the velocity profile turbulent in the turbulent flow regime, in the same way you can define how we get the mass transfer concentration variation when you are talking about the mass transfer in the turbulent flow. You have to write the time smoothed equation of continuity, that is gradient of V plus will be equal to 0. You have to write down the equation of motion, all the time smooth quantities. So, these will give you the equation of motion, this is the time smooth equation of continuity. I am just writing down all the equations when you will be having, apart from the flow, hydrodynamics, you will be having a mass transfer regime. Equation of continuity for species A, that means it is basically component balance of species A under the flow condition you will be having the convective variation of concentration of species A on the left hand side, and on the right hand side you will be having the diffusive variation of concentration, like J bar laminar, it is basically the Fickian diffusivity. This is obtained from the Fick's law. You will be having a corresponding term for the turbulent flow, the mass flux due to the turbulent flow, and there will be plus minus reactive terms, either plus or minus, depending if your component is generated by some reaction, then it will be a plus, it is a source term. If your component A is consumed in the reaction, then it will be a sink term in your equation. Now, this DAB is diffusivity of species A in the solvent B. Now, these is basically physical property of the liquid, of the solute. Now, the mass flux corresponding to the turbulent term, turbulent flow or turbulent mass flux, again you cannot quantify them exactly from some concrete theoretical basis. There will be some correlations or empirical relations, those will be available, which will be relating it with a concentration gradient or velocity gradient or both. Those will be inserted in the equation and you will be getting the corresponding concentration profile. Now, let us look into some of these empirical equations. The first one is eddy diffusivity. This is analogous to Fick's law. This is known as the turbulent diffusivity or eddy diffusivity. This will be like the Fickian diffusivity. Fickian diffusivity is basically physical property of the system, of the solute, but this will vary with the location. This will vary with the concentration. This will be varying with the basically location, right? So, these are basically an empirical constant which will be fitted to the experimental results, and the value of this diffusivity will be at least 3 to 5 order magnitude higher compared to the Fickian diffusion. That is why you will be getting higher mass flux in case of the turbulent flow. much higher magnitude compared to Fickian diffusivity, which will be basically the property of solute. So, you will be getting an enhanced mass flux or enhanced transport of species A under turbulent flow conditions. The second relationship of turbulent mass flux is Prandtl's mixing length. So, again you will be having basically different types of empirical relations for the turbulent mass flux. This one is like the kinematic viscosity or kinematic viscosity corresponding to the Eddy terms previously. Okay. So, you will be having the expression from the that you will be obtaining from Prandtl's mixing length. You will be having expression of the turbulent mass flux corresponding to von Karman's relationship, and of course Dirichlet's relationship. So, depending on the application, whether you are computing your mass flux close to the wall or away from the wall or in the turbulent in the center of the pipe, you will be using the appropriate relationship, integrate if possible analytically, if not do it numerically, and you will be getting the concentration profile. And remember, once you do, in order to obtain the concentration profile, your it is coupled with the velocity profile, because the convective terms are there. So, you have to solve first the velocity field and take the help of the solution of the velocity field, insert the expression of the velocity in your equation and obtain the concentration field. Similar for the temperature field. In order to obtain the concentration field, you have to write down n minus 1 number of species balance equation. The last one will come from the overall energy mass balance, but for the energy temperature, in order to get the temperature variation, you have to solve only one equation, that is the energy equation. So, your Prandtl's mixing length for the turbulent mass flux will be equal to minus L square. L is basically ky, y is the distance from the wall multiplied by velocity gradient multiplied by the concentration gradient. So, you have to insert the velocity, the gradient of velocity that you have already obtained previously in order to get the concentration profile. The third one is von Karman's relation. The turbulent part will be minus k square. This part will be related to the velocity field. Again, this k is an empirical constant, it is roughly equal to 0.4, and you will be having Dirichlet's relation. Close to the wall. Now, depending on your situation, you have to use one of these equations. If you are working close to the wall, then you will be working with the Dirichlet's relation. If you are working beyond that, you may be working with the Prandtl's mixing length relation or von Karman's relation. But the difficulty with using the first one, the Eddy diffusivity one, you do not know the value of eddy diffusivity. You know it is order of magnitude higher, but how much higher? Higher. Suppose your molecular diffusivity is let us say 4 into 10 to the minus 9 meter square per second. We know the eddy diffusivity will be 3 or 4 order of magnitude higher than that. But what exactly? Whether it is 3 order of magnitude higher, whether it is 5 order of magnitude higher, that is really not known. So, you have to conduct experiment and do a theoretical analysis and fit the experimental result with the theoretical prediction, and by optimizing of the experimental profile, you can estimate the unknown DAB. But the other equations like Prandtl's mixing length etc., these values of numerical constant, empirical constants are already known. This n equal to 0.124, this k is roughly 0.4 in von Karman's or in Prandtl's mixing length analogy, and in Dirichlet's relation this n equal to 0.124. All the other quantities are known, either they are independent variable or they are dependent variable. So, it is easier to use them in order to get the concentration field. This is the time averaged one. Okay. Now, I will give an expression for turbulent flow. In a tube with constant mass flux in A0 at the wall, the profile becomes Ca plus minus Ca1 plus is equal to 1 by K1 ln S plus by S1 plus for S plus greater than 26, and Ca plus equal to 0 to S plus ds plus 1 over Schmidt number Now, we can take the same kind of analysis as previously and obtain the concentration field. This will be in the turbulent core beyond the viscous sublayer, and this includes the viscous sublayer as well as the buffer region. For viscous sublayer, Ca plus the non-dimensional concentration becomes Schmidt multiplied by the S plus for S plus is less than equal to 5, and Schmidt it is a dimensionless number. It is known as Schmidt number. Mu by rho DAB, and DAB is basically the molecular diffusivity, which is the property of the solute. And this molecular diffusivity is a physical property of the solute. Now, we will be doing derivation for energy equation as well. Okay. Either this in this class or I will start in this class only, and after completing all the turbulent flow the basic materials like in the in order to get the velocity field, in order to get the concentration field, to obtain the temperature field. Okay. So, we will be solving couple of problems by doing different types of relationships and how to use these relationship in order to get the velocity field or concentration field or temperature field. So, after that we will be complicating the equations, and probably in the next class, in tomorrow's class, we will be doing the energy equation and how the energy equation will be simplified in order to obtain the temperature field. In tomorrow's class only, most probably we will be having time in order to solve couple of problems. I will be solving one problem that I have given in the last year mid sem or end sem, I do not remember, and using different types of analogies. Basically, whatever we have done in this class, all these universal velocity profiles, these logarithmic profiles are obtained if you use Prandtl's analogy. But if you use von Karman's analogy or if you use the other analogies, how the expression will look like, that must be known to you. And if you compute taking 2 or 3 empirical relationships and then you compute numerically, then you will see you will be getting almost close velocity profiles or concentration profiles or temperature profiles. So, you can use any one of these relations 4 relations that we have discussed so far. So, any of